Continuing on with section 6.6, our next example, expand each expression as much as possible and simplify, and to do that we need to really make use of the properties right here. So recall natural log base a, provided a is bigger than 0 and not equal to 1, of 1 is always 0. Whenever those match, the base of the log and the base of the exponential, they undo each other. And if I'm looking at an exponential in which the base happens to match the base of the log, and log is the power, they undo each other as well. So when I look at problem number part A, example A, well, I have a couple of options. The best option to really make use of that is for me to say, you know what, this is log base 3. I left some space so I could write with ease and not squish anything out. That will be 3 squared, and based on the second property, the base and the log, the base of the log and the base of the exponential match, they kind of undo each other and you're left with a 2. The next problem, again, couple of options. One option is for me to use the second law. Say that's log base 3 of 1 minus log base 3. And I do know that 27 is 3 cubed. Log base 3 of 1 is 0 minus 3. And my answer will be negative 3. There is another way I could do this problem, and that would be for me to say, you know what, that is the log base 3 of 1 over 3 cubed. Move this up by properties of exponentials, that becomes a negative 3. Those undo each other and I'm left with a negative 3. So either or will do. That's not a problem. This method or this method will work. On example C, I'm going to say this is the log base 3 of 9 plus the log base 3 of x squared. I'm already aware that 9 is 3 squared, that's a 2, and I could move the 2 up front and say that's twice the log base 3 of x. Next example up, I could say this is the log base b, and I could write square root of b as b to the 1/2, and by the second property of logs, those undo each other, so to speak, and that's a 1/2. I look at example E. I'll say that's the log base 10 of x plus the log base 10, and I could write a cube root of x, the cube root of x minus 4 as x minus 4 raised to the 1/3. That would be the log base 10 of x plus, and again, by the third law of logs, that's 1/3 the log base 10 of x minus 4. And if I take that last example, that is the log base e of 5 x to the 1/5 minus the log base e of x minus 3. We have no rule for a minus. Don't mix that with the division. I could say that's the log base e of 5 plus the log base e of x to the 1/5 minus the log base e of x minus 3, and that would be the log base e of 5 plus 1/5 the log base e of x minus the log base e of x minus 3. Now whenever you are expanding logs, you want to try and get a log of a linear term if possible. Not that it's wrong if you don't, but that's normally how it works. Now, something I wanted to point out about the last two examples if you look in the back of the book, you will notice if you have such a problem, that's what they would write. And if you look at this problem, you'll notice they would write this as, and you would be thinking, what's wrong with the answer? Nothing's wrong. Your calculator can read two logs, log base 10 and log base e. So, instead of writing a base 10, you simply write a log. It's understood that if you give a log note, every log has a base. If you don't give it a base, you're saying that the base is 10. And if you see a log with a base e, you would write it as a natural log, ln of x. A very useful log that we're going to use both of those. Now, since the calculator can only read log base 10 and log base e, we have a formula, change of base formula, which says if you have a log of a base other than a 10 or an e or a base that you don't like, you could write that as natural log of b, which is the argument, over natural log of the base, or log base 10 of the argument over log base 10 of e, or simply log of any base of your choice. You could choose the base to be anything you want as long as they match. So in the next 3 examples, and that's the conclusion of this section, we want to solve these problems using a calculator. This problem is saying, what power do I raise 5 to get a 7? Well, you would say, well, there is no such thing. Yes, there is. If you think about this, this is an exponential equation. If you can't solve the exponential equation, what you do, if you recall, we log both sides. What base should I use? Okay. I'm going to give this a bit more space. That's what I messed up on. Here we go. So, yeah, I give a space on the right, but not on the left. So what I'm going to do, I'm going to take the log of both sides. You could do that to the entire side, not the pieces. I'm going to elaborate on that later on. What base should I use to get rid of the exponential? Well, to make use of the second property, log base 5. There it is. I got x to be log base 5 of 7. Well, we have a problem. I don't know what that is. Well, I could either write this as natural log of 7 over natural log of 5, or I could use log of 7 divided by log of 5. And if I get my calculator out and take natural log of 7 divided by natural log of 5, that would be my answer. I want this approximated to 4 decimal places. 1.2091. 1.2091. Remember the rounding. Wherever you're going to stop your rounding, if the number to the right is 5 or more, you would round up. And if you decided to choose log of 7 divided by log of 5, it doesn't matter, you get the same answer. And now let's check. Take 5 and raise 5 to the 1.2091. You'll notice we're going to get a number a bit bigger than 7 because we rounded up, and it's accurate to 3 decimal places because this is rounded. And if I look at part B, the same idea applies. Say, okay, well, I can't seem to solve that. What I'm going to do, I'm going to log both sides. What base should I use to eliminate the exponential? The base of the exponential. I can log both sides with the same base. So my x equal log base 5.32 of 22.3, and the same trick again. I like to use natural log because it's 1 letter less, nothing more. You're welcome to use whatever you want. And if I round this again, I'll get my calculator, and that would be natural log of 22.3 divided by natural log of 5.32. And in this case, I'm getting 1.8574. 1.8574. And you could always check your work if you want. You don't have to, of course, but you could check your work. That is, take the original problem, take 5.32 and raise it to the 1.8574, and we're going to get 22.300, and again after that you're off because you rounded up. And if I look at the last example I have, I would log both sides. Again, the base should be 2.74, and that would mean x plus 2 equals log base 2.74 of 0.871. And to get x, I would have to solve, and that's not a problem. Just subtract 2 from both sides, and my x will equal natural log of 0. Again, you could use any base that you want. It would be wise to use what your calculator can read, and that would be simply, again, I could plug the whole thing in my calculator, and I'm looking at a natural log of 0.871 divided by a natural log of 2.741, and I'm gonna subtract 2 from that. That's negative 2.1370. Now, I do have a warning. I did mention I was going to talk about that. If I have 2 to the x plus 3 equal 5, you could log both sides, but in this case, that will be used. There. 2 to the x minus 3 equal 5. Well, I could log both sides, but that would be useless. That is, if I log both sides, I can't use the change of base formula because that's not going to get me anywhere. So definitely something not to do. That's why whenever you want to use the definition, you want to make sure that you have the exponential by itself on one side, everything else on the other side. And another mistake that students do, that's also never allowed. You can never do that in math and choose base 2. That's not allowed either. You could log the entire side. You can't log the individual terms. That's not allowed. And that concludes this section.